We are going to be solving logarithmic equations. To solve logarithmic equations or equations containing variables in the logarithmic expression, we're going to, of course, use for help the exponential equations. So the steps are the following. Express the equation in the form solved for the logarithm. Solve the single logarithm equal to a variable. Then we're going to be applying the rule for converting to exponential form, or we always start from the base, go the base times what's across the equal sign, and go back across the equal sign. After that, we are going to solve for the variables. Now there is a trick here. We must check all the solutions in the original equation, because as we know, the domain of the exponential function is all real numbers, so the answers may be numbers that make the logarithmic function not to exist. In the logarithmic function, we know that the domain is only greater than 0 numbers. So example 11, we're gonna think about how this looks like in exponential form. We always start from the base. 3 powered by across the equal sign is equal to across the equal sign, or we figure that x is equal to 3 to the 4th, which is 81. So must check here, not like in the previous cases. I occasionally check just to see if I've worked correctly, or for the logarithmic equation I must check. I must make sure that my answer is possible. Plug in x to be 81 and use a calculator or property of logarithms. That's logarithm base 3 to the 4th, and based on properties of logarithms, this is equal to 4, so I have worked correctly. Example 12, again apply the property of logarithms. It's solved for the logarithm already, so that's always start from the base. 5 powered by 2 is equal to x plus 1, or 5 squared is 25, is equal to x plus 1. Subtract 1 from the other side, x is equal to 24. I forgot to circle my answer. And here, before I circle my answer, I make sure that I check. Is logarithm base 5 of 24 plus 1 equals to 2? Well, that's logarithm base 5 of 25, and indeed 5 squared is 25, so the answer is equal to 2. So I'm going to square my answer. Now for example 13, I cannot do that until I don't use the properties of the product property of logarithms. I need to combine those two logarithms in a single one, and we do that by going logarithm base 4 of the product of the functions that are inside the logarithms. So here you go, and that's together inside that logarithm. Based on exponential properties, that means 4 powered by 2 is equal to x plus 3 times x minus 3. X plus 3, x minus 3, that's a formula. If you don't know the formula, you are going to distribute. X times x is x squared. X times negative 3 is negative 3x. 3 times x is positive 3x. And 3 times negative 3 is negative 9. Those two cancel. This is why it's formula, because they are always middle terms, so it always cancels. So 4 squared is 16. So we end up having x squared minus 9 is equal to 16. I'm gonna add the 9 to the other side of the equation, and x squared is gonna be equal to 25. Now take root of both sides. There are two solutions. X is equal to 5 and x is equal to negative 5. All quadratic equations have two solutions. Let's check if those are possible. Check. For x is equal to 5, logarithm base 4 of 5 plus 3 plus logarithm base 4 of 5 minus 3. Well, this is logarithm base 4 of 8 plus logarithm base 4 of 2. Use the product property, logarithm base 4 of 8 times 2, which is 16, and of course 4 squared is 16, so it checks. However, if we use x is equal to -5, we'll see that there is a problem with even the first one plugging in, because we end up having logarithm of negative number. Well, that's a no-no. That logarithm cannot be taken of negative numbers, so -5 is going to be extraneous solution, which is solution of the quadratic equation, but is not solution of the logarithmic problem. So there is only one solution, and this is x is equal to 5. Next question. It's been solved for the logarithm already. Notice that this is a single logarithm to this side, so I can apply directly going to exponential form. That's 2 powered by across the equal sign is equal to across the equal sign. That's again quadratic equation. I'm gonna solve by going x squared is equal to 2 to the third is 8 and minus 4 to clear x squared by itself, or x squared is equal to 8 minus 4 is 4. This means x is equal to +2 and -2. Check. And the check, you cannot go, you may decide not to go to the very end, as I did over here. What is important is to make sure that those arguments are positive. Make sure that you don't end up having negative numbers, as in this case. So I can see that if x is either positive or -2, since logarithm base 2 is to be taken of this argument squared, I would always end up having a positive number. So that's logarithm base 2 of 4 plus 4 is 8, and indeed 2 to the third is equal to 8, so 2 works. Similarly, if we plug in x is equal to -2, logarithm base 2 of -2 squared plus 4 is gonna end up being again logarithm base 2 of -2 squared is 4, 4 plus 4 is 8, and we end up having the same issue. So it turns out that both of those numbers are solution, and there is no extraneous solution. For question 15, again we have two logarithms, so we need to combine them in a single logarithm using the product property of logarithms. So logarithm base 6, multiply the arguments, x plus 3 times x plus 4. Make sure that logarithm is taken out of those, both of those is equal to 1, and then apply the exponential, convert to exponential function. Always start from the base. 6 powered by 1 is equal to this product, and now start multiplying. X times x is x squared, x times 4 is 4x, then 3 times x is 3x, and 3 times 4 is 12. I'm gonna subtract the 6 from the other side of the equation to form a nice quadratic equation here. X squared, that's my positive 7x, and 12 minus 6 is positive 6 equals 0. So we're going to solve this quadratic equation. X squared plus 7x plus 6 equals 0. Now we're going to use factoring here. It's easy. to factor, that's x plus 6, x plus 1. That means x needs to be either negative 6 or negative 1. Now we need to check. Plug in x to be negative 6. Negative 6. We're going to feel that this is not a good solution, even plugging in only one part of the problem, because we receive a negative number inside the logarithm, which is a no, not possible. And check with x is equal to negative 1, logarithm base 6 of negative 1 plus 3 plus logarithm 6 of negative 1 plus 4. That's logarithm base 6 of 2 plus logarithm base 6 of 3. We can combine those as logarithm base 6 of 2 times 3, which indeed is equal to 1. I'm going to move here, be able to write my 1. So we end up having one solution, x is equal to negative 1, and x is equal to negative 6 is going to be extraneous solution. It is solution to the quadratic equation, but is not a solution to the logarithmic equation. One example with subtraction of logarithms, we can combine them again through properties of logarithm. This is logarithm base 4 of quotient of x plus 2 and x minus 1 to be equal to 1. And then again we go use properties of exponents. 4 to the 1 is equal to this fraction. We're going to multiply both sides of this equation with x minus 1 to free the denominator. And so I'm going to continue right here. 4 times x is 4x. 4 times negative 1 is negative 4. 4 minus 1 and x minus 1 and x minus 1 cancel, so x plus 2 to this side of the equation. Subtract the x and add the 4. We end up having 4x minus x is 3x, and 2 plus 4 is 6. Divide by 3, x is equal to 2. And I can see that plugging in both cases 2 and 2, I'm not getting any negative values, so I hope if I worked correctly I have gotten the correct answer. Let's see, logarithm base 4, x being 2, that's going to be logarithm base 4 of 4, minus logarithm x being 2, that's going to be logarithm base 4 of 1. Logarithm base 4 of 4 is 1, logarithm base 4 of 1 is 0, or altogether 1, so my answer checks. That's one type of the equations versus related with the logarithmic equations. Another type is when we have two logarithms to the other side. In this expression, types of problems, we're going to be using again the property that the logarithmic function is one-to-one, similar to the exponential form. And if we have logarithm base 2 of x to be equal to logarithm base 2 of 3, for example, obviously x cannot be anything else but 3. Example 17, we see that log 5 is exactly the same to both sides of this equation, so that means the insides of this logarithm must be equal. solve this linear equation by subtracting 3 from both sides. 11 minus 3 is 8. Divide by 2, x is equal to 4. Make sure you check again. That's gonna be logarithm base 5 of 2 times 4 plus 3, which is logarithm base 5 of 2 times 4 is 8 plus 3 is 11. Is that equal to logarithm base 5 of 11? Yes, and it's correct, so it checks. So I'm gonna circle my answer. Example 18. Again, I have two logarithms. Log base 3 is the same to both sides, so we can cancel these parts. The only thing we want to make sure is that the arguments are equal. Subtract x from both sides. It's going to be 6x minus 12 equals 0. Add 12 to the other side. 6x is equal to 12. Divide both sides by 6. X is equal to 2. The only thing I need is to check if I work correctly. Logarithm base 3 of 7 times 2 minus 12. Is it equal to logarithm base 3 of x, which is 2? And indeed, 7 times 2 is 14 minus 12 is 2. So that answer checks. Now for example 19, we cannot continue before we take care of that 2 here. And it's in multiplication with x, so it comes as an exponent for the x. Logarithm x squared is equal to logarithm 4, and just a reminder, that's common logarithm. So log part is the same, meaning x squared needs to be equal to 4. This equation has two solutions, x is equal to plus or minus 2. However, if we check with x is equal to negative 2, in the original problem, we see that we would have a negative 2 as argument, which is not possible. So negative 2 is going to be extraneous solution. And if we check with x is equal to 2, that's 2 times logarithm of 2, which is logarithm of 2 squared, and I'm receiving that logarithm of 4, which I was needing. So x is equal to 2 is the only solution. X is equal to negative 2 is extraneous solution. Example 20. Again, to apply this method, I need to have just one logarithm equal to one logarithm from the other side. So combine those two logarithms through a quotient rule for logarithms. It's going to look like logarithm of x plus 7 divided by 3 equals logarithm of 7x plus 1. Now we have exactly the same logarithms from both sides. We're going to remove the logarithms part and make the x plus 7 divided by 3 equal to 7x plus 1. To remove the denominator, I'm going to multiply both sides of this equation with 3. And that 3 would remove the denominator. So x plus 7 is equal to 3 times 7 is 21x. And 3 times 1 is 3. I'm gonna subtract x from both sides and subtract 3 from both sides. We'll end up having those cancel out. So 7 minus 3 is 4. 21x minus x is 20x. 3 and 3 goes away. Or x is equal to 4/20ths, which divide by 4 can be simplified to 1/5. So x is equal to 1/5. Of course, I need to check. And logarithm of 1/5 plus 7, and it's not that much about me checking if numerically it's correct as is it possible to be plugged. So I see that there is no any problem of plugging in 7/5 plus 1. I can see that all arguments are possible, so most likely if I continue simplifying, I'm gonna see that x is equal to 1/5 is a solution. And with this, I'm concluding this video.